In this presentation, we're going to look at random number generation, which is a sort of introduction in itself to Monte Carlo simulation and stuff like that. A sequence of pseudo-random numbers from a uniform distribution over the interval 0 to 1. Now, this is quite frequently used. In fact, it's one of the fundamental building blocks of this subject area. Has been generated by a computer. Okay. Explain the advantage of using pseudo-random numbers, which is this approach using an algorithm from a computer rather than generating a new set of random numbers each time. Now, okay, this question actually is historic in nature. So it's a sort of like, it looks at the old way of working with random numbers, which would actually, that they would be generated on a big computer and published in books, and that you pick them, the numbers out from books. Okay, it's like a phone book essentially of random numbers. Okay, they were truly random. They were sort of tested scientifically, and they were used in scientific research before the age of computers. What you do is you pick a page and, let's say, pick the last 3 digits or the first 3 digits from one particular line, and use that as your random numbers sequence. Okay, now we enter the age of computers, so this means that we can use programming languages to simulate random numbers. Now, the thing about random numbers when they are generated by computer programs is they're not exactly fully random. Okay, they are actually generated by algorithms. Okay, so, and they can be replicated. Okay, for example, if you look at programming languages, they have a thing called a seed, which is a particular default setting. That means that if you want to replicate a selection of a set of random numbers, you can specify the seed such that you get the same set of random numbers each time. It sort of specifies the algorithm that generates the random numbers to start at a certain place. Okay, or start with certain conditions. Okay. Anyway, let's just answer the question properly. This type of question is going to be seen less and less, because I think the idea of using a published physical copy of a tables is going to be less and less frequent. But anyway, using pseudo-random numbers removes the variability of using different sets of random numbers, which is helpful for comparing different models. Okay. Sorry, what's the question actually? Just go back to the question. Explain the advantage of using pseudo-random numbers rather than generating a set of random numbers each time. Okay, so that first bullet point is essentially that you can sort of specify the settings, okay, and that you would be able to sort of have the same set of random numbers for 2 different models and sort of see how both models approach each other. So it allows for this comparison, basically, is the key thing there. Okay, only a single routine is required for the generation of pseudo-random numbers, whereas in the case of truly random numbers, we need either a lengthy table, the big book I was talking about, or software enhancement to a computer. Sorry, hardware enhancement to a computer. Okay, which is like how these tables were generated historically. Okay. So, yeah, it's essentially a computer program can do it, and it's one of the things that people will now be able to do with programming languages like R or Python, is to generate random numbers. Okay? And if we wish to use the same sequence of random numbers in 2 models, we only need to store the seed, which is the sort of initial conditions that I was talking about, for the pseudo-random numbers, as opposed to a record of potentially millions of truly random numbers. Okay. So that's it. Now, the second question is, let me scroll back up. Use examples to explain how a sequence of pseudo-random numbers can be used to generate simulated observations from a continuous distribution and a discrete distribution. Okay. So, in the first instance, what we do here is we can generate, using some sort of computer program, a number between 0 and 1, a real number between 0 and 1. Okay, so for example, 0.23456, and this is the type of thing that a computer can do. Now, each number between 0 and 1 is equally likely. Okay, that's an important point. So anyway, what we do here is we allow this number between 0 and 1 to be, in effect, our cumulative distribution function. Because remember, a cumulative distribution function also has the range 0 to 1. Okay? So what we do is essentially work backwards. So we set u as the value that will give us this cumulative distribution function value for x. Okay? So 0.25, okay, so this is actually roughly the quartile, the first quartile for x. So essentially what we do is we start off with this, allow it to equal this, and then work backwards to find x. Okay, so x is the inverse of the cumulative distribution of the number that we've just randomly selected from the uniform distribution. Okay, so a well-known example will be the exponential distribution. Okay, and so this is the cumulative distribution function there, 1 minus e to the minus lambda x. So we let u equal to that. Okay, and then what we can do there is just mathematically rearrange it such that we will get an expression like this. We solve for x. Okay, now something actually I just to sort of remark upon here is I sort of skipped. I went from here to this in one fell swoop. I don't want to spend too much time in it. The reason is that actually that's worth a presentation in its own right. The thing is, though, actually, just a sort of quick remark, and you're going to sort of spot this every so often in these type of questions. U and 1 minus u can be used interchangeably. So, for example, in an equation, you can substitute out u and put in 1 minus u and vice versa, because they are drawn from the same distribution with the same parameters and they will have like the same characteristics. So what might happen is that when you're deriving one of these expressions, it is perfectly conceivable that you may replace u with 1 minus u or vice versa to simplify the expression. Okay, so this is just a sort of quick remark. This is correctly log 1 minus u over minus lambda. Okay, that's what we actually would get when we solve that. Okay, but what we do there is replace 1 minus u with u because we're not losing anything in the algorithm. Okay, whereas it's a quick bit, it's that one bit's a little bit simpler to solve. Okay, that's a very important point actually with this topic. The second question here is what we do here is working with the integers, find x such that it's based on the cumulative distribution functions here. Okay, it's using steps of the cumulative distribution functions or ranges of the cumulative distribution functions. Okay, this is a very important equation here. Okay, and I've messed it up. That should be x minus 1 there. Okay, not x. But essentially that's the approach we take. So what you do is you'd be given a probability distribution and you set up a tables like that, and what happened is that it divides up the range of values between 0 and 1 into certain categories, certain intervals based on the cumulative distribution function, and what happens is based on the random number that you would generate, you would pick out which of the ranges you are in, the intervals that you were in, and assign the random number that corresponds to that interval, and that's your random number. Okay, very quick example. Suppose we have a binary outcome. Okay, x equals 0 if u is less than 0.5, and if u is greater than 0.5, you have x equal to 1. Okay, now I won't spend too much more time in that because I'm going to do a few of these examples of both the continuous and the discrete, so we'll leave it there.